So this rectangle, okay, you revolve it. So you revolve it, okay. So revolve it around this axis, okay, around this line. Around this line. So here you revolve it, okay. So you revolve it actually here we can open what? We can open a right circular cylinder, okay. So here, okay, now we can see here is a triangle, so here is a rectangle, here is a rectangle. So this rectangle we revolve it, okay. So we revolve it, okay. So we revolve it by this line, okay, by this line. So we can open it a circular cylinder, okay, cylinder. So this is the first one, and for the second one, for here is a semicircle, okay. Here is a semicircle. For this semicircle, okay. For this semicircle, we revolve it, okay. Revolve it along this line, along this line. So we can open this solid sphere, okay. Solid sphere, okay. So this is the second. For the third, okay. For the third here is a triangle. Here is a triangle. So for this triangle, we revolve it around this line, okay. Around this line, around this line. So you can see we can open a solid core, okay. A solid core. So here go on, okay. Go on. So here is a triangle, or here is a rectangle. Here this rectangle, okay. This rectangle revolving around this line, okay. So in this case, we can open this hollow right circular cylinder, okay. Circular cylinder, okay.
Yes.
So this is some solid by opened by what? Opened by the revolution, okay. Revolution. So by this revolution, so here now we need to introduce how to compute the volume of the revolution, okay? The volume of the solids of revolution. So here we give a let f be a continuous non-negative function of AB, okay? Let R be the region that is bounded above by y equal to fx, and below by x-axis, okay? Below by x-axis, and undersized by the lines x equal to a and x equal to b. So now we find the volume of the solid of revolution that is generated by revolving the region, okay? The revolving the region R along the x-axis, okay? Along the x-axis. So we revolving it, okay? Revolving it. So revolving R. So we can see actually here, and we cut. So revolving it, we open this formula, okay? We will open this figure. So for this figure, so for this solid, okay? For this solid, we cut it, okay? We cut it along the x-axis, along the x-axis. So it's easy to see that, okay? You cut it. Because here is revolving, okay? So you cut it actually each closed section, okay? Each closed section is what? Each closed section actually is a circle, yeah?
Yeah.
It's a circle. So actually here we need to find the area of a circle, okay? The area of a circle. Yeah, the circle. Yeah. So we need to find the area of the circle. So actually we just need to find the area of the rulers, yeah? So the rulers actually is this part, yeah? So this part actually is what? This part actually is fx, yeah? So here means at each x, the closed section actually is a circle, and the rulers of the circle actually is fx. So here means what? So here means that actually the ax equal to what? So ax, okay, x is the area of the closed section. So x actually equal to pi times fx square, okay, fx square. So from here, so we know Ax, so the volume, okay, so the volume actually P actually equal to what? P equal to the definitely equivalent of Ax from A to B, yeah? So, and Ax equal to here, Ax equal to here, so here actually equal to the definitely equivalent of pi fx square dx, okay, dx from A to B, okay, so this is the formula, okay, so this is the formula of the volume of solid of revolution, okay. So here, so now, so here we can obtain this formula, okay, we can obtain this formula. So now we give an example. So find the volume of the solid that is obtained by when the region under the curve y equal to the square root of x over the interval from 1 to 4, okay, is revolved about the x-axis, okay, the x-axis. So here for the example 2, okay, here means the curve, okay, the curve actually is y equal to the square root of x. Here is x, here is y, here is the origin, so y equal to the square root of x. So here is y equal to the square root of x, and from 1 to 4, okay, from 1 to 4. So this is r, okay, so this r actually, okay, this r revolving around the x-axis, So here means that this fx is the square root of x, yeah, the square root of x. So the volume, okay, so the volume actually equal to what? So the volume actually equal to the square of the definite equivalent of pi fx square dx. Here fx is what? Here fx is the square root of x, yeah? So the square root of x, so here equal to what? So here equal to the definite equivalent of pi the square root of x square dx. So the square, so here a equal to what? A equal to 1, b equal to 4, yeah? So here is from 1 to 4, So the square root of x square actually is x. So here is from 1 to 4 pi x dx. So pi is a constant that moves through the equal sign. So here equal to pi from 1 to 4 x dx. So what's the antiderivative of x?
X squared over 2.
1/2 x squared, yeah?
Yes.
1/2 x squared evaluated at 4 minus evaluated at 1. Okay? So here equal to pi times 1/2 4 square minus 1 square by 2. Okay? So here is actually 16 minus 1. So 15 by 2. Okay, 15 by 2 pi. So this is the result. Okay, 15 by 2 pi. Okay. So this is the first. Now for the second, okay, we need to derive the formula for the volume of a square of radius r. Okay, of radius r. So now we can see what we need to find the volume of a square. Okay, a square of radius r. So we know that the square actually is we can see matrix. Okay, here. The square, okay, the square actually we can open it by revolving a semicircle, okay, revolving a semicircle around the x-axis. So here we can see here is the x-axis. Here is the x-axis. So here is a semicircle, okay, of rulers r. So rulers r. So here is the arc semicircle, okay, the arc semicircle. So here is r. Here is minus r, okay, minus r. So we revoluting, okay, we revoluting the semicircle around the x-axis. So we can open a sphere, So the volume of a sphere actually is the volume of revolution. So here we need to find this line, okay. So this line actually equal to x squared plus y squared equal to r squared, yeah. And actually here is arc semicircle, okay. Arc semicircle. So here y actually equal to what? So from here we have y squared equal to r squared minus x squared, yeah? And because here is arc semicircle, so here y actually is non-negative, yeah? Non-negative, so here means y equal to what? Y equal to the square root r squared minus x squared, yeah? So here we use the formula, okay? We use the formula v actually equal to what? V actually equal to here is from minus r to r, yeah? From minus r to r, and here is pi fx squared. Here fx, okay? Here fx actually is y, yeah? So here equal to minus r to r. Here is pi the square root r squared minus x squared. Here the whole square, yeah? The whole square, so dx. So this is the formula, okay? So this is the formula. So here the square root square, okay? So actually here this part actually is minus r to r. Here is pi r squared minus x squared dx. So here pi is a constant. Can move through the integrand sign. So here actually equal to pi minus r to r. Here is r squared minus x squared dx. Yeah? Here, so now we need to find the antiderivative of r squared and x squared. So r squared actually is a constant, yeah?
Yes.
So what's the antiderivative of a constant?
It's constant.
So here is pi, here is r squared x, yeah? So the antiderivative of r squared actually is r squared x. So what's the antiderivative of x squared?
X cubed plus 3.
1 plus 3x cubed, yeah? So this is antiderivative of this function. So from what? From minus r to r. So evaluate at r minus evaluate at minus r, okay? So equal to here. So now we compute it. Here is pi. Here is r squared times r minus 1 by 3 r cubed. Okay, so this is the first. And the second is minus pi. Here is r squared times minus r. Okay, minus r. And minus 1 by 3 minus r cubed. Okay. So here r squared times r, so r cubed. Okay. R cubed minus 1 by 3 r cubed. So here this part is 2 by 3 r cubed. Okay. So pi times 2 by 3 r cubed. Okay. So here r squared minus times minus r. So minus r cubed. Minus r cubed. So here is minus r cubed. So here is the minus r cubed. And minus r the whole cube. Okay. Actually it's minus r cubed. Minus r cubed. So here is minus minus. So here is plus 1 by 3 r cubed. Okay. So minus r cubed plus 1 by 3
Minus.
r cubed. So here equal to minus 2 by 3 r cubed. Yeah?
Yeah.
So this part is minus 2 by 3 r cubed. So here is minus minus, so here is plus. So plus pi 2 by 3 r cubed. So the result actually is 4 by 3 pi r cubed. Okay, so this is the formula of the sphere. Okay, the volume of the sphere.
Wait, can you just explain again how you found 4 by 3 pi r, please?
Yeah.
Yes, after that step, how do we find it?
So from here. Yeah. Here actually it's you let x equal to r. Yeah. So here is this r. And minus this function evaluated at minus r. So minus here minus r. So the easy to here is r squared times r, so r cubed. R cubed minus 1 by 3 r cubed. So here is 2 by 3 r cubed. So the first part actually is pi times 2 by 3 r cubed. So here is r squared times minus r. So actually this one is minus r cubed. Yeah? Minus r cubed. So here is minus r the whole cube. So the minus r the whole cube actually is minus r cubed. Minus, so here minus, so here plus. Plus 1 by 3 r cubed. Minus r cubed plus 1 by 3 r cubed. So it's minus 2 by 3 r cubed. So here means that here this part is minus 2 by 3 r cubed. So minus, so plus. So here plus pi 2 by 3 r cubed. So here this 2 parts, so it's 4 by 3 r cubed. So this is the second, okay, so this is the second.
R squared x is there. Where yeah, just last line. Yeah, this line I did.
So this is the function. So we is the fundamental. So this function evaluated at r minus the from
There to there.
from here to here. So this one. This one, yeah? So this one actually equal to pi minus r to r. So here is r squared minus x squared dx, yeah? So here actually equal to pi minus r squared dx minus r to r x squared dx. Yeah? So here r squared is a constant, yeah? So here actually equal to pi. So constant moves to the integral side. So here is r squared minus r to r. Here is 1 dx. Yeah? So minus r to r x squared dx. Yeah?
Okay, last
So this is the volume of the revolution, okay, revolution. So now we can see we have another, so means the volume by washes, okay, washes perpendicular to the x-axis, okay. So here for this case, here we have two functions, okay. So we have two functions. Here is the first. Let f and g be continuous function and the non-negative function on the closed interval a b. And suppose that fx is greater than gx, okay? Fx is greater than gx for all x in the interval a b. So let r be the region that is bounded above by y equal to fx, below by y equal to gx, and the other side by the lines x equal to a, and the x equal to b, okay, the x equal to b. So here means that R is this part, okay, this region. So now we need to find the volume of the solid. We need to find the volume of the solid of revolution that is generated by revoluting the region R about the x-axis, okay. So here this is a little complex, okay. So actually here you revolute it. So you revolute it around the x-axis. So we obtain this solid, okay? This solid. So this solid, so here we can see this solid, okay? So this solid, so we can cut it, okay? We can cut it along the x-axis. Along the x-axis, we cut it. We cut it, so we can, it's easy to see each closed section actually is a circle, or is a circle, we have a hole. Yeah, we have a hole. We have a circle, okay? A circle with a hole, okay? With a hole. Yeah. So here we can see actually each closed section, okay? Each closed section actually is a circle. We have a hole here. We have a hole here. So we can solve this problem by slicing. For this purpose, observe that the closed section of the solid taking perpendicular to the x-axis at the point x is the annular, okay, the annular or the y-sharp, okay, the y-sharp region with the inner rulers gx and the outer rulers fx. So here means that the area AX actually equal to the area of the outer circle, okay, pi fx square minus the area of the inner circle, okay. So the inner circle is the pi gx square. So the AX, the area, so the AX is actually equal to pi times fx square minus gx square, okay, gx square. So here, so for this case, okay, for this case, we have the volume, okay, we have the volume actually equal to the definite integral of pi fx square minus gx square from a to b, okay, from a to b. So for this case, okay, for this case, actually here we have b equal to the a b, the definite integral of x from a to b, okay. So here ax equal to pi fx square minus gx square, okay, gx square. So this is the formula, okay, so this is the formula. So here we use this formula, okay, this formula. For this formula, we give an example, okay, we give an example. So find the volume of the solid produced by when the region between the graph of the equation fx equal to 1/2 plus x squared and gx equal to x over the interval 0 to 2, okay, is revolved by about the x-axis, okay, the x-axis. So here we first plot the graph, okay. To plot the graph, here is x, here is y, here is the origin. So here first, okay, the first is fx equal to 1/2 plus x squared. So 1/2 plus x squared actually is like this, okay. Here is 1/2 Here is y equal to 1/2 plus x squared. X squared. So we just in the interval from 0 to 2. Okay, from 0 to 2. So here is 2. Here is 2. Okay, here is 1/2. And now for the second, gx equal to x. Okay, gx equal to x. So here, gx equal to x. So when x equal to 0, gx equal to 0. When x equal to 2, so gx equal to what? Gx also equal to 2, yeah? So here actually like this. So here is y equal to x, okay? Y equal to x. So now the region between these two curves actually is this part, okay? Is this part. Is this part. So now this region, okay? So this region we will rule it about the x-axis, okay? About the x-axis. So here we can see we cut it, okay? We cut it. So it's a washing, okay? So it's a washing. It's a washing. So for here we cut it, okay? We cut it. So for here is x. Here is x. So here actually is so this function square minus this function square, okay? So here fx, for fx is this function, gx, the lower, the above function is fx, the below function is gx, okay? So here the b actually equal to the definite integral of pi times the up function square. Up function is 1/2 plus x squared, okay? So here is 1/2 plus x squared. The up function square minus the below function square, okay? So the below function is y equal to x, this function, okay? So minus x squared. So here, so dx. So from what to what? From 0 to 2, yeah? From 0 to 2. So here is 0, here is 2. So now we need to find this definite integral. Okay, this definite integral. So here, pi is a constant moves through the integral sign. So here equal to pi, here is from 0 to 2. So here we open it, okay, we open it. So here 1/2 square, 1/4, plus x square actually is x square x to the 4th power, yeah, and plus 2 times 1/2 times x squared, so it's plus x squared, and minus x squared dx, yeah. So x squared minus x squared, so cancel, okay, cancel. So here actually this is equal to what? So this is equal to pi, the definite integral of 1/2 or 1/4 plus x to the 4th power dx. From 0 to 2, okay, from 0 to 2. So we need to find antiderivative of this function. So here, what's the antiderivative of 1/4? So it's pi times 1/4x. So what's the antiderivative of x to the 4th to the 4 power?
X to the 5th power 1/4.
X to the 5 power by 5. Yeah?
Yeah.
So here is 2 evaluated as 2 minus evaluated as 0. So here equal to pi times 1/4 times 2 plus 2 to the 5 power by 5. Okay, by 5. And evaluate 1/4 times 0 plus 0 to the 5 power by 5, okay? So here this part is 0, so this part, okay, this part. So this part actually equal to pi times, here is 1/2 plus 2 to the 5 power. 2 to the 5 power is what? 2 to the 5 power is what?
64.
64? 2 to the 5 power. 2 to the 5 power?
22.
Oh, no, 32. 32.
22, yes. So here is 22 by 5. Okay, 22 by 5. So here we make them have the same
Denominator.
denominator. Yeah. So here equal to pi times 10, 5 by 10 plus 10. Here is 34 or 64. Okay. So here equal to 69 by 10 times pi, okay? Times pi. So here is this part, okay? So here is this part. And of course, sometimes, okay, sometimes we have the volume by distance, and the watch is perpendicular to the y-axis, okay? To the y-axis. Just now actually it's perpendicular to the x-axis, okay? Here is perpendicular to the x-axis, okay? So now actually we have sometimes we have the by y-axis, okay? By y-axis. By y-axis actually it's the same, okay? We have a curve x equal to mu y, x equal to mu y. So the region. So where are you going?
Large. Can you see the second? X is the point. Second.
I didn't know now, I just go watch.
Yeah, no, I know. So you are comma, yeah? I know, but you the second class. You are,
No, Lavshay, second class I did, Lavshay, say that. Lavshay, I did. He thinks that's when you've come back. You explain.
yeah, what's your question?
Second number.
So you open it, yeah? Open it, so here this part square is 1 by 4. This square is x square is x to the fourth power. So here 2 times 1/2 times x squared. So here is x squared. So you know a plus b squared equal to what? You know a squared plus 2ab plus b squared, yeah? So here 2 times 1/2 times x squared, so it's x squared minus x squared. So x squared minus squared. So cancel, yeah? So this is actually this part. So this part, so here the antiderivative of 1 by 4 is 1 by 4x. The antiderivative of x to the fourth power is x to the 5 power by 5. Yeah? So now, this is the case for the perpendicular to the x-axis, okay? So sometimes we have the perpendicular to the y-axis, okay? To the y-axis, so it's like this, So here we have a region, which is bounded by x equal to mu y and the y-axis, and y equal to c, y equal to d, okay? So we revolute the region R along the y-axis, okay? Along the y-axis. So here we want this solid, okay? This solid. So for this solid, okay? For this solid, we cut it along the y-axis, okay? Along the y-axis. So here area of the closed section actually is pi mu y uy square. So actually in this case, the volume of this part actually is V equal to the definite unit of pi uy square from C to D. Okay, from C to D. And for this case, actually it's the same. So here R is the region belong the left curve. Okay, bounded by the left curve, x is equal to mu or by, and the right curve, x is equal to wy. Okay, from y to C and y to D. So now we revolute the region R. Okay, revolute the region R around the y-axis. Okay, around the y-axis. So here we can open this solid. Okay, this solid. So for this solid, it's the same. Okay, it's the same. So what's the volume? What's the volume is the definite integral of pi times wy square minus vy square. Okay, vy square. So actually, this case is the same. It's similar to this case. Okay, to this case. Here now we introduce the last one example. Okay, find the volume of the solid produced by when the region enclosed by y equal to the square root of x and y equal to 2 and x equal to 0 and x equal to 0 is revolve. Okay, about the y-axis. Okay, about the y-axis. So here we plot the graph. Okay, we plot the graph. Here, for this case, okay, so here we need to plot the graph. The first is y equal to the square root of x. Here is x. Okay, y, okay. And so first, y equal to the square root of